Question 26 is a nice question because it just shows kind of like ingenuity. And I like ingenuity, right? So I'm sure that somebody tried a lot of stuff before they kind of came up with this sort of idea. There are other ways that you can find the antiderivative of secant. For most people, it's just like looking it up on the internet. But if we didn't do it this way, there's other ways to do it. So the kind of the idea here, the sneaky thing is that if I multiply this by secant of x plus tangent of x over secant of x plus tangent of x. And I could do that because this is equal to 1, right? So I'm not changing my antiderivative at all. I could then distribute this secant to get secant squared of x plus secant tangent of x all over secant of x plus tangent of x dx, right? So it might be kind of tough to figure out what the best u would be in this point. Because if I say, hey, u is secant squared, well, that doesn't really have a nice derivative. If I say tangent, what that's secant squared, but I still have all those little secants hanging around. But you might notice up on top that the derivative, that secant squared and secant x tangent x are kind of familiar, right? Secant is the derivative of tangent. Secant x tangent of x is the derivative of secant. Oh, that's what's hanging out in the denominator. So if we let u equal secant of x plus tangent of x dx, then du is secant x is secant of x, tangent of x, and the derivative of tangent of x is just secant of x. Secant squared of x, that's what I said. Right, so this whole entire numerator now is this. So this whole entire integrand becomes the antiderivative of 1 over u du, aka the natural log of u, aka the natural log of the secant of x, plus the tangent of x, plus a constant hanging out at the end. Isn't math